Today we'll be dealing with the other topic, that is periodic classification. You might be coming across this chapter when you were in school also, because anyone who is pursuing science, especially chemistry, must be aware of periodic classification because the entire chemistry revolves around it. So I would consider that anyone who is good at periodic classification is rather good at chemistry, because the entire chemistry revolves around what? The periodic classification. If such is the importance of periodic classification, then a student who is looking at this classification thinks that it's just rows and columns, and all these metals and the non-metals are the elements which is being discussed by his teachers back school, right? They think that, it has been placed in an order in rows and columns, right? That's what is the first impression, what you get it once you look into the periodic classification. You must understand that, right? Yes, it is rows and columns. Yes, it is rows and columns. But what you are not understanding here is, it is a serious thing. There is some, degree of, depth involved in it when the classifications are being done, right? Now, first of all, the common sense is, if you are going in for any classification, forget about the chemical classification, that is the periodic classification. Well, when you're going in for any classification, there must be some basis. You just cannot go in and classify things, in the classroom also. When someone is classifying some of the students who play, there is a classification, then the basis might be sports or intelligence or whatever. There must be basis for some classification. Now, what is surprising even for me is basically periodic classification. When you actually see, it's not so trivial as you think. Let me quote, it's not so trivial as you are thinking. The classification has a lot of depth. You must understand that. Yes, it might be rows and columns for you, but actually if you look into the top research organizations, when you enter straight from the indoor of a great scientific institution, let it be any scientific institution, which is dealing with chemistry, then I think at the in way itself you can see a periodic classification chart has been displayed on the in-gate itself, right? That signifies the significance of this classification. It's not that someone gave you some metals, some non-metals, and you have placed them in an order or something like that. Let me induce into you the degree of seriousness in which the classification has been done. Let me tell you that, in fact, I would like to write it for you. So it is so serious affair. Classification is not that simple. It is a so serious affair, this periodic classification of placing them in rows and columns. The serious affair is, rather, I would like to call, in fact, this periodic classification, in fact, remember, it stimulates research. It stimulates research. Let me tell you this. So if someone is thinking that it is so trivial classification of elements that are present on the surface of the earth, and someone has placed in rows and columns, and they have just taken a scale and a pencil and have done this, and for them, I wanted to tell you that it basically stimulates research. Such serious is the classification. You must understand that. Now, what do you mean by stimulating research? Well, I'm using a bigger word, stimulating research. Now, what do you mean by that? What is very strange and surprising and wonderful, in fact, it's wonderful in the case of, the classification done by people for us, it's so beautiful, rather, is suppose, now what do you mean by stimulating research? That's what I'm focusing on. Now, suppose tomorrow, after 20 years of your research, of your career, 25 years, you are actually able to find out a new element. Assume that you have found out a new element, because all elements are not found out at the same time, right? So there is a scope for further elements being placed in the periodic table, and assume you have done that after 30 years, you have found out some element somewhere, and then you wanted to, search space in the periodic table, and let me tell you then, the space is fixed right now. The space is fixed for that element right now. So when we actually look into the periodic table, there is a great basis. There is a great basis in which it has done. And the basis will lead to, it in fact stimulates what? Research in doing, and based on the basis in which the periodic classification has been done, that creates a way, and it stimulates your mind to go in for research for other elements, and if you find it right, and that element has a place in the periodic table 20-25 years before the element has been found, and people have named it to be X, Y, mystery element, whatever you might be calling it, I think that element has a place in the periodic table. So overall, what I'm telling is, don't make this classification trivial. You must understand that it's not a trivial classification. It stimulates research. And let me tell you, in this particular chapter, what we will be doing is, on what basis the classification has been done. That's number one. What is the basis? When you actually postmortem this basis, then you get into several things. You must understand that. That completes the chapter. So what you're doing here, is, I appeal to anyone who is looking at periodic classification and you wanted to write some exams based on that, and everything I'll be linking it to the exam, what you will be writing, and I would like to highlight that or put it in a box, and those things must be remarked by the students in the ongoing lecture. Right, let's slip on to the topic now. So I am telling you that it is a serious classification. It doesn't have, and don't make it a tag of a trivial thing of this classification. There is basis. It's not a dream of anyone. And they have done it, and when you actually get into the depth of the periodic table, in fact, you will find that there is a way it will stimulate you to a research. That's what I wanted to induce the seriousness into you. Now, coming to the point, right? Now, you have around 125 to 130 elements approximately in the periodic table, right? 130 elements in the periodic table. And someone is asking me a question. What is the difference between, what is the basic difference? Don't tell many differences. You tell me one basic difference between all these elements, 130 to 125 elements that are placed in the periodic table. What is the basic difference? Well, if you ask me, what is the basic difference? Or otherwise, if someone is more specifically asking me, what is the difference between lithium and what is the difference between sodium? What is the difference between sodium and what is the difference between iron? And what is the difference between iron and there's some other F block element or the D block element or the S block element or whatever? You must understand, what is the difference? Well, if you ask me what is the difference, then I would like to tell you, first of all, that, it is basically atomic size. Well, let me tell you what you mean by atomic, size. Now, lithium, if you take any element, right? If you actually see, it will be having a set of properties. Similarly, sodium will be having a separate set of properties. Similarly, an F block can be having a separate set of properties. Well, all these properties, this I'm speaking of chemical properties. You can have physical properties, the melting points, boiling points, or their physical states, or whatever, the physical as well as the chemical properties which I'm speaking of the basic difference of these chemical properties is basically everything boils down to atomic size, mind you that. So, if a simple question is asked, what is the difference between all the 130 elements in the periodic table? Well, I would like to simply say that it is atomic size. It is the size which will determine the properties of a particular element or a block or an S block elements or a P block elements or individual elements or anything. So if someone is asking what is the difference, don't think here and there, it's basically atomic size. So what I will do when I say atomic size, well, watch carefully here. If this is the case, atomic size is so critical. So let us understand what is atomic size, right? So before that, I would like to say, now here, when I'm starting this chapter, you must understand that I am not getting into the older forms of periodic table. I'm just sticking on to the one which is the modern periodic table, which is essential for you to write exam, right? I'm not getting into the Doberaners. I'm not getting into the Mendeleev's classifications. These are obsolete now. They're obsolete now. They're something like, history. They have attempted it to do, and somewhere in the middle when they are doing it, some positives are there, some negatives are there, but I think mostly negative. So these classifications of Mendeleev, these classifications of Doberaners and other attempts made by people are obsolete, and those will not be asked in your exam. So what we will do is we'll stick to modern periodic table. And what I'm telling is, and what I'm basically telling is, everything boils down to what? Atomic size. So what I will do, right? What I will do is, what is atomic size? Let us understand this. What is atomic size, right? And before that, here is a brief you must understand here. I wanted to write something, right? The chemical, comma, and I want the attention of everyone. The chemical, comma, physical properties, mind you, the chemical and physical properties, whatever they are exhibiting, the elements, the chemical as well as the physical properties are basically functions of atomic number. Well, that's what is a modern periodic law. So I call this to be a modern periodic law. Well, there were many attempts earlier, like, Dobereiner has done some triads formulae for classification, and then came Mendeleev. He was telling that the physical and chemical properties are functions of atomic weights rather, right? So you must understand it's a function of atomic number. It's not about mass number. So you must understand it's all about what? Atomic number, says the modern periodic table. So forget about Mendeleev and other classifications. The modern periodic law says, if I can read it for you, the chemical and physical properties are functions of what? Atomic number. So what is basically telling us, and this is done by Moseley. Moseley's modern periodic law. Moseley's modern periodic law. And the basis of classification is atomic number. And let me tell you that the basis, all classification done, the basis is atomic number. Atomic number, and not the other ones like atomic weights or something like that, where earlier people have done it and they are somewhere in the midway, they failed to classify all the elements. I think the modern periodic table are all functions of atomic number. Now what is atomic number? It's number of protons that are available inside the atom. That's what is called atomic number. So when I say physical and chemical properties, you must understand each and every element will have physical and chemical properties, right? And they are all dependent upon atomic number. Atomic number, you must understand that, right? Now what is, let us come to the point. Let's come to the point now. Now you understand that I was actually telling you that an atom has infinite number of shells, infinite number of orbits. And in periodic classification, as the name is telling you, in periodic classification, here I highlight what I'm telling. Here I highlight, and this also forms the basis for the classification. Remember, each period, I'm drawing the attention of everyone. Please understand that each period in the periodic table, is a shell. Mind you that each period in the periodic table is a shell, and the shell proposed by what? Bohr, which is designated by the principal quantum number with values n value 1, 2, 3 and so on up to infinity, because you must understand you have infinite number of shells. And I'm claiming, I draw the attention of everyone please before I slip onto the topic. And now I'm basically claiming that each period is a shell. Each period is a shell. You must understand the horizontal lines in the periodic table which you see form the basis of classification, as it is called periods. So I'm telling you what is a period. A period is nothing but the shell proposed by Bohr, which is designated by a principal quantum number and n value equal to 1, 2, 3, like that, infinity. So I'm basically telling that if the number of shells are infinite, let me tell you in the periodic table, even the periods will be what? Infinite. That's why I say the periodic table is incomplete. It's basically incomplete. That's what I'm claiming that 20, 30 years after, if you are able to find any element, right, then that element's place in the periodic table is fixed. It is basically fixed. You must understand. That's because the atom has infinite number of shells, and each shell is basically a period. You must understand. So the horizontal lines what we see are nothing but what? Periods. You must understand this. So the Bohr's non-radiating path, the Bohr's shell, the Bohr's orbit, all these are nothing but what? Periods. So if you see here, before I rub this, let me tell you that, before I draw that, let me tell you that, the classification is not simple, man. It's not simple. It rather stimulates what? Research. You must understand. There are n number of people who have attempted earlier, but I think they have all become obsolete. And the one which is available to you now, which will be asked even in the exam, is nothing but the modern periodic table. And the law states that the chemical and physical properties are functions of what? Atomic number, not atomic weights, or triads, or something like that. It's basically nothing but what? Atomic number, Z, which is nothing but the number of protons that are available. So all the properties of the elements which are exhibited in the periodic table, all properties exhibited, physical or chemical, are all dependent upon what? Atomic number, and that forms the basis for classification. You must understand that. The second thing what I'm telling is, each period is a shell. The same shell which is proposed by Bohr, which is designated by the principal quantum number n, whose values extend to infinity. So you can expect even periodic table number of periods, that is the horizontal lines, also being what? Infinite. So if I can give you an idea, then it is like this. So the classification is done on the basis of periods. That's why we call it to be a periodic classification. The horizontal lines are important, not the vertical lines, because each period, each horizontal line is basically nothing but what? It's nothing but what? A period, right? So I can simply say, the periods, each period what I'm drawing, 2, 3, 4, 5, 6 and 7 periods you have in the periodic table, and 18 groups. So all these 7 periods, right, and you have 18 groups in the periodic table. You can continue to draw 18 periods in the periodic table. Well, that vertical lines have no significance. You must understand the basis in which it is constructed or framed is nothing but on the basis of periods. And when I say this, these ones are nothing but shells, and this is n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, 5, 6 and 7. And they continue because the 7th period itself is incomplete. So you have 8th, 9th, 10th. I think you have a lot of scope for elements to be actually getting evolved, and then you have a place fixed in the periodic table. That's wonderful, and it even surprises me even at this stage. You must understand that, right? So you have basically 7 periods and 18 groups in the periodic table. It's almost like you can say the extreme left are S block. I think just I'm briefing it. You might be knowing it, but before I go into details, I think this geographic thing is important. So it is extreme left is S block, and extreme right is what? P block, and in between you have your D block, and then when you come down from the main frame of the periodic table, then you have F block. So S will be having 2 blocks, that is 2. P will be having 6. So you have 6, so total is 8, right? Total is 8, and then in the D block you have 10, then it is what? You have 10, so that is 18. That is the 18 groups which I am claiming in the main frame of the periodic table, right? And there are 2 series which are placed they are picked up from the main frame. So that is lanthanide and actinide series. They also belong to the shells itself. But for maintaining decorum, which I will tell you, right, they are actually placed out from the main frame of the periodic table and placed at the bottom, right? Let's now slip on to the topic. So remember, S block 2, P block 6, it is total 8, and in the D block you have 10, and then when you go out from the main frame of the periodic table you have 2. So total 18 groups and 7 periods is what the periodic table is consisting of, and the periodic table itself is what? Incomplete, and there is scope for other elements being added in future. You must understand. If this is the case, let us slip on to the topic. Let us basically slip on to the topic. You must understand this. Watch carefully here. Now there are it must be great harmony. There must be great harmony in the periodic table. So there are some properties of these elements. Now, what are the properties of these elements, right? Mind you, all the chemical and physical properties are functions of atomic number. No more atomic weights and all these things. We stick on to what? Atomic number. Right? There are some properties which repeat themselves at regular intervals. There are some properties called periodic properties, like the law of octaves, right? So if you say sa re ga ma pa da ni sa, so it's like a law of octaves where it's actually coming back to you, right? Similarly, you have several properties in which they will be what? Repeating themselves in the periodic table. And we would like to take one by one. And if I can list it out for you, then it is nothing but atomic size, which repeats itself at regular intervals, atomic size. Then you have your electronegativity, electropositivity, right? Electron affinity. All these are nothing but what? Periodic properties which repeat themselves at regular what? Intervals. You must understand this. They repeat themselves at what? Regular intervals. And what we are supposed to do is, these things which I can say: atomic size, electropositivity, electronegativity, electron affinity, and many other things. How do they fare in a period? How do they fare? And what is a trend in a period and in a group will be questions in the exam. Well, I'll be simple. At the same time, we will get into the depth of the subject also. So I draw the attention of everyone and I start it off from what? From what? Atomic size. Atomic size. Now what I'm trying to do here, what is the trend? What is the trend? What is the trend? Trend of atomic size. Trend of atomic size in trend of atomic size in periods and groups. Trend of what? Atomic size in period and groups. Because why did I choose atomic size in the first place? Atomic size forms the fundamental thing. If you ask me what is the difference between all the 130 elements in the periodic table, I would like to simply say it is size. Nothing more than that. If you are small in size, your properties are different. You're big in size, your properties are different. You are very small, then your very properties are different. You're very big, your properties are different. So the entire chemical and physical properties also depends basically on one factor That's atomic size. So why don't we take it up in the first place and check out how the size varies in a period, how the size varies in a group. But before that, if I can define what is atomic size, then I would like to define it like this. What is atomic size? If I can define, then understand this. Understand. Distance from nucleus to the outermost shell. Look into this. Distance from the nucleus to the outermost shell. Now, a thinking which I was inducing into you when I was lecturing atomic structure is basically understand that electron itself is an orbit. Electron itself is a shell. Electron itself is a stationary orbit, or electron itself is an NRP. Don't think electron is different, shells are different, orbits are different, orbitals are different. If there is no permanent paths around the nucleus which are laid down, as we have tar roads outside, or the cement roads outside where people don't walk, but still the roads exist. So you understand that the electron revolving around the nucleus, the path itself is an electron, the path itself is an orbit, the path itself is an orbital, the path itself is a non-radiating path. You must understand this. Don't distinguish these two and see. Right? If that is the case, when I say distance from the nucleus to the outermost shell, I also mean it's nothing but the electron. Well, we look into this definition. He is asking us, start from the nucleus, get down at the outermost shell, take a scale, take a pencil, then draw it. You're supposed to get atomic size. Well, it's wonderful theoretically. Theoretically, it's great. Rather, there is nothing we are not able to follow here. So it's basically telling its distance from nucleus to the outermost shell. That's what he is basically telling. So this is nucleus. You start going, and to drop at a particular shell, this is nothing but what? Atomic radii, or the atomic size, what he is telling. So atomic size, or I call this to be atomic radii rather, synonymously. So we are basically discussing the trend of what? Atomic radius, or the size, you can say synonymously. So you must understand, it is simple to understand. Distance from the nucleus to the outermost shell. Shell is nothing but the electron, and that's nothing but what? Atomic radii. Wow, wonderful. There is absolutely nothing in this. But remember, this definition is without any confusion. But what is my issue, or everyone's issue, must be atomic radii. This definition, well, watch carefully what I'm trying to understand. This definition of atomic radii, that is the distance from the nucleus to the outermost orbit, the definition of atomic radii seem to be purely theoretical. Purely theoretical. It's purely theoretical and absolutely ideal. Absolutely ideal. It is absolutely ideal. You must understand this. What are you telling me? You're telling me take an atom, cut it with a cutter which is available in the kitchen, then open it up as you do it in the case of watermelon. Then you take a scale, then you put it at the nucleus, go to the first orbit, and then find the measurement. Well, we can understand this, but this is absolutely ideal. This is absolutely ideal because of several reasons. So do we think that it is as simple as that, you start from the nucleus to the outermost orbit? No, it's not simple. So this definition is just fit for hanging that and hanging up as a board, but absolutely nothing operational in this. Absolutely nothing operational in this. So what we will do is we'll get into some operational definitions rather than sticking on to what? Ideal definition. This is where I slip on to the topic, and that is where you must be focusing on. So before I start it off, what I'm discussing is atomic radii. Now, why are you discussing atomic radii in the first place? I'm discussing it because all the properties depend on what? Atomic radius, and the definition says it's a distance from the nucleus to the outermost shell. If this is the case, then this is how atomic radii is defined, but I have a serious issues cropping up with this definition, because he is telling us something that you catch hold the atom in your hand and then cut it off and then take a scale and measure it, and then you will get atomic radii. I think no one in the world where people cannot see an atom through a naked eye is able to do this. You must understand this. When atom itself is not visible, you speaking of, measuring it to the outermost shell is absolutely theoretical and it's ideal, right? So what to do? Shall we run away? No, we don't run away. Let us actually check it out. Some operational definitions. Let us see that. So basically, this definition of atomic radii seem to be absolutely ideal. Absolutely ideal. And ideal things doesn't exist. Of course, yes, they don't exist because atom itself is invisible to the eye. So what are we doing? Shall we run away? No, absolutely, we don't run away, because we are now searching for what? Operational definitions. Now I'm slipping onto the topic. The other was introduction. Now I'm actually slipping onto the topic now, which will be significant for your writing for your exams. So I draw the attention of everyone. Right. So when you wanted to get away from an ideal thing, then you will have to face a consequence. You will have to face a consequence. What is the consequence which you are supposed to face it? Watch carefully here. Watch. Well, I'm actually slipping onto the topic which will be important for you while writing exams, right? If this is the case, look into this atomic radii. And I call this to be the first periodic property. This is the first periodic property which I'm discussing. That is the first periodic property. Periodic property is that which repeats itself at regular intervals in the periodic table. That's what is called a periodic property. And let me tell you that, when I was defining this atomic radii, you were telling that it is distance from nucleus to the outer shell. When I say outer shell, it is electron. Shell is no different from electron. Both are same. No electron, no shell. No electron, no shell. That notion, you please remove it from your mind when you are in the higher classes. It's fine when you are in a 7th class to understand what is a shell, right? But at the same time, you understand now no electron, no shell. So when someone is telling distance from the nucleus to the outer shell, then I'm speaking of electron. Well, if this is the case, this definition is absolutely ideal. Absolutely ideal. So, if you want the correct measurement, if you wanted the correct measurement of atomic radii, there is absolutely no other way. You have to catch hold of the atom, cut it into 2 pieces from the nucleus, take a scale and measure. Then only you will get correct measurement. Absolutely, 100% without any error. And I wanted to tell you, if you want zero error in the measurement of atomic radii, if you want zero error in the measurement of atomic radii, then you are supposed to take an atom, cut it off, take a scale, and then measure it off, right? If you want zero error. So what I'm telling is absolutely ideal, and such measurement, and I'm telling if possible. Well, I would like to underline this. Well, if possible, such measurement of the distance of the nucleus to the outermost shell, if it is possible, then it will have zero error. Zero error. Well, I'm happy. But the issue is any deviation, whatever might be the reason, any deviation of you not catching the atom in your hand, then cut it off and measure with a scale. If you deviate from any of these procedures, don't tell me any complaints. Don't tell me any complaints. if you deviate, any deviation from the above definition, which is ideal, well, watch here, which is ideal, induces error. You must understand, it induces error. What I am telling, if you wanted a zero error, stick to this definition. What is the definition? You start off from the nucleus, go to the outermost orbit, then if you are able to do it, this is atomic radii, and the measurement will give you zero error. If you are so perfect, do it. Please do it. Go and do it. What are you trying? What are you doing? You are asking me to take an atom in my hand, cut it off with a cutter which is there in your kitchen, open it, take a scale from the nucleus to the outermost orbit, you find it, na? You find it off. When you find it off, then you get zero error. Zero error. Do it. If you do this way, then you get zero error. But I'm warning you, the warning is, any deviation from such above definition which is ideal will induce error. Well, let me tell you first of all the difficulties in this. As I told, ideal things don't exist. You please understand, the first difficulty is, first of all, atom is invisible. You taking in your hand and cutting it off is ridiculous. It's absolutely ridiculous. Catching your atom in your hand and cut it with a cutter in the kitchen and open it off is absolute nonsense. Ridiculous. Ridiculous, rather. So, if it is ridiculous, then what to do? What to do? I am telling that if you're not taking an atom in your hand and cut it off with a cutter, then you will have error. If you cut it off, take an atom, cut it off, no error. If you are unable to do it, for some reason, sir, atom is not visible to me or something like that, then you induce error. So what I mean by all this is, while measuring, right? While measuring atomic radii, right? The following difficulties arise. Of course they will arise. Who will take an atom in their hand? Ridiculous. It's not visible. And if at all you take also, you are supposed to cut it with a knife. Not possible. So you are encountering the following difficulties. What is that which are difficulties? If I can list it out first difficulty, isolating an atom difficult. Isolating an atom is what? Difficult. You must understand. It is absolutely difficult. It's not visible to a naked eye. So when I say this, isolating an atom is difficult, you started deviating from the original definition. You're starting deviating now. Start deviating from the original definition. That's number one. Suppose, assume for a moment you are a Superman and your eyes have great magnification and you have actually taken the atom and isolated. Assume. Ridiculous, but assume. If that is the case, you are telling, start from the nucleus, go to the outermost shell. And what does the shell contain? Electrons. Both are same. Right? You are asking me to first locate the electron. Locate the shell. Start from the nucleus and then go and locate the electron or the shell, which is ridiculous. In fact, laughable. Right? Why it's laughable, ridiculous, is the second is, first of all, you have Heisenberg's uncertainty principle in place. You have Heisenberg's uncertainty principle in place. What are you talking about? You start from the nucleus, locate the electron and go there and take a measurement. Where Heisenberg says it's impossible. It's impossible to determine the position of an electron or the velocity of the electron at the same time. You must understand this. It is impossible. Ridiculous. So someone telling you, start from the nucleus, go to the outermost shell, take a scale, and all seem to be absolutely ideal. Absolutely ideal. Because what happens is isolating the atom itself is difficult, number one. It's impossible rather, right? And the second one, you locating the electron, which is a subatomic particle inside the atom. The issue is exactly. You can say that, you can tell any value, but the issue is what? Being exactness, right? Being exact is the issue. So the first one which crops up is what? Isolation of an atom is difficult. Second thing is it's Heisenberg's uncertainty principle. It's impossible to locate the position of the electron with accuracy. And the third one, understand electron is like a cloud. Is like a cloud. Cloud. And let me tell you, with a irregular boundary. Right, electron is like a cloud with an irregular boundary. I think you might have seen clouds outside. Do they have a round shape? Did anyone see a cloud with a regular boundary? Did you see any cloud with a regular boundary? Yes, in schools, the electron is drawn like this. Here is the nucleus, and here is the shell, and electron is drawn something like this in your books. Round. But that is for your understanding. Remove that from that perception from your mind. Because we told that electron is like a wave. If electron is like a wave, it displaces from the mean position. Because wave does displace from the mean position, and the maximum displacement it goes is also called amplitude. So if electron can be viewed as a wave, you're thinking that it will be having a round as drawn or printed in the textbooks is absolutely ridiculous. And mind you, the electron is a cloud with an irregular boundary. It doesn't have a fixed boundary. It's so irregular. The electron is something like this. It's like a cloud. It's cloud. It is having an irregular boundary, man. It has an irregular boundary. Your definition of atomic radii says, start from the nucleus, get down at the electron's position, take a cutter from the kitchen and measure it off. Wow, the definition is super. But does it make sense while getting into the operational mode? Absolutely not. Ridiculous. Because we encounter all these difficulties. You must understand this. One, isolating atom is difficult, first of all. You cannot isolate it. Second is the Heisenberg's uncertainty principle, which says that impossible to determine what? The exact position. And then the third is more worrying. Electron is like a cloud with an irregular boundary. And also I would like to add to this, 4, I can say the electron cloud has a diffusing property. A diffusing property. You must understand. It has a diffusing property. Well, if it's a cloud, if you think that electron is a cloud, electron will be diffusing. Right? It will be diffusing like this because it's moving away from the mean position. After all, it's like a wave. When someone is diffusing, doing like this, relaxing, then you asking me to come down from the nucleus, get down to the outermost shell, locate it, and I diffuse like this. Where are you measuring? What is this definition of start from nucleus to the outermost shell becomes a major issue. So the basic hurdles what you face is this, and of course electron has a diffusing property. You must understand it's not so neat and clean for you that it is a nucleus. Here is a permanent path for you. It's no permanent path. It's not like a cement road outside where you don't walk also. The road won't disappear the next day. Here is an electron. This itself is an electron. The path itself is an electron, mind you. Mind you. So both are synonymous. The electron and the orbit, both are what? Synonymous. You don't have a permanent paths laid for electrons to revolve as we have roads outside. So not everything is neat and clean for you. So it is nucleus till here, measure it off. This is atomic radii. Such definition seems to be absolutely ideal, right? But we have an issue. We have an issue. The issue is, even though we are shouting on the idealness of the definition, but if you try to deviate from what he is telling, distance from the nucleus to the outermost shell, due to various reasons, you can't do it. Due to various reasons, if you try to deviate, that induces error. That induces error. Mind you, if you deviate from this definition, that will induce error. That induces error. That induces error. That induces error. Error. This definition, the way of doing it, if you deviate from it due to various reasons, what are the reasons? This. If you deviate from that, then you have induced error. You have induced error. Then question arises, what to do? The answer is simple. You can't do anything. You have to live with error. You must be living with error. There is no other way. You can't do this. You can't do that. You can't do that because of this. Because of this, you are unable to do that. So those becomes ideal. Ideal things give zero error. And you're trying to deviate it. When you deviate, then you are inducing error. So there is no other option at all. And let me tell you now, let me tell you now that atomic radii definition is absolutely ideal, cannot be measured. So what I'm telling, and cannot be measured due to what? Due to various reasons. Hence, error induced. Hence, error is what? Induced. You can't do anything. Hence, error is induced. And we are supposed to live with what? Error. You are supposed to live with what? Error. There is absolutely no other way for you. You must understand. Now it's a common sense. It's a common sense now. If someone is telling you there is no other go, you have to live with error. You have to live with error. Then our entire focus will shift now. The entire focus will shift now. How to what? How to what? Minimize error. How to minimize error? Because first of all, inducing error itself is a wrong thing. Because I can't measure the atomic radii ideally from the nucleus to the outermost shell. It's impossible. So I have induced error. When I have induced error, I have to live with it. If you have compromised on that, then our focus at least must be legitimate. The legitimate thing, what you're supposed to do, even though you have error, you must be trying to what? Minimize the error. Minimize the error. Such that the atomic radii measurement is basically accurate. You must understand that. So what I will do, hence in your textbooks or in the exam, he will be asking these. So what I'm trying to tell, since the definition is absolutely ideal and cannot be measured the way he told, then error is induced. And we have to live with the error. Now the only thing left is we are supposed to be legitimate. Legitimate in the sense how to minimize the error. Don't try to eradicate error. It's foolish. I will eradicate error. If you eradicate error, that means you're speaking of an ideal definition of atomic radii, which is impossible. Because you have Heisenberg's uncertainty principle, you can't locate an electron exactly, and you have the isolation of atom itself is what? Difficult. So don't claim that I will eradicate the error and all these things. It's impossible to do it. When you can't eradicate, you have to live with error. When you're living with error, you can't be complacent. You should be legitimate. And the legitimacy is basically simply how to minimize it. Right? If that is the case, and hence, watch carefully, and hence, I propose operational definitions. Hence, I propose operational definitions. Hence, I propose operational definitions, practical definitions. Practical definition, not like this bloody, your ideal word, definition. You must understand. Hence, I propose operational definitions for atomic radii. Operational definitions for atomic radii. And what are the definitions? If I can list it out, due to these difficulties, I propose operational definitions for what atomic radii. What are the operational definitions? Watch carefully here. I'm rubbing it off, right? And let me tell you that this definition is absolutely ideal, right? And it cannot be measured, so error is induced. You have to live with error. The only option left for you is minimizing error. And when you minimize the error, then you are actually proposing the operational definitions for atomic radii. Now, what are the operational definitions? Watch carefully here, right? The operational definitions for measuring atomic radii are: 1, the covalent radii, 2, the ionic radii, 3, the van der Waals radii, and 4, the metallic radii. If you ask me, what are all these? These are all operational definitions. That means that you deviated from what? Your basic definition of atomic radii. So I can simply say all these measurements of atomic radii, shall have errors. And these errors are minimized to maximum. They are legitimized errors, right? So, what is strange, a student who is actually listening to the lecture must understand. We are defining atomic radii. We couldn't do that. So now we are proposing 4 operational definitions. Not 1, 4 operational definitions. That means we are encountering problems. And we have covalent, ionic, van der Waals, metallic to measure the atomic radius of all the 130 elements in the periodic table. So one thing which I would like to induce, as we have hurdles in measuring atomic radii, the first thing seems to be significant. Isolating atom is difficult. If that is the case, if you have proposed 4 operational definitions and you say the errors are minimized, how did you minimize the error? Well, I would like to say there is a basis for even proposing the 4 operational definitions, right? So if you take one atom, right, its isolation is difficult. The isolation is difficult. Then what the proposal was, then take 2 atoms. Come on, man. If you take 1 atom, you will have 0 error. If you take 2 atoms, then the error is induced. What to do? You can't isolate 1 atom. It's not possible. So isolation of 1 atom is not possible. Then take 2 atoms. 2 atoms. Error is induced. We have to live with error. But the only thing left is we have to minimize the error. Instead of taking one atom, if you have taken two atoms, then error is induced. How do you minimize an error? Now the issue is, when you take two atoms, take two atoms. But to get accurate, not accurate, we can't use this word accurate, but but getting error minimized, ensure these two atoms are as close as possible. As close as possible, you must understand. If you can't take one atom, then take two atoms. Then if you take two atoms, you can't place one atom there, one atom here. You must understand that the atoms must be as close as possible. As close as possible. Why as close as possible? Because we want to reduce the error. We want to minimize the error. So I want atoms as close as possible. And I wanted to understand, when is the situation in chemistry? When is the situation in chemistry? I'm asking you the question. When is the situation in chemistry when atoms are too close? Well, atoms are very close to each other when they are actually participating in bonding. Remember what I'm trying to tell. One atom isolation difficult. So you have taken two atoms. When you have taken two atoms, error is induced. Because atomic radii is something which is related to atom, not two atoms. So once you take two atoms, error is induced. If error is induced, you can't help it. You have to live with it. You have to minimize it. For minimizing, I am ensuring that the atoms are very close to one another. The situation when atoms are very close to one another, when they actually participate in what? Bonding. And let me tell you, in chemistry, we have no one bonding. Do we have one bonding? No, absolutely not. When atom participates in bonding, you have several bondings, several forces. And hence I propose four operational definitions. Why? Some people participate in covalent bond. Some people participate in ionic bond. Some people don't participate in bonding at all. Like inert gases. They don't participate in bonding at all. For them I propose van der Waals radius. There are some metals which you have metallic bonds. A metallic bond. Metals are solids. They touch each other. The atoms touch each other. In such cases, I propose what? Metallic bonds and metallic radii. Look into the sequence. Look into the sequence. One atom isolation difficult. Rule it out. When you rule one atom out, then error is induced. When you want to live with error, you have to minimize it. And for minimizing it, what I'm doing is, when the two atoms you are taking, instead of one atom you have taken two atoms, then you have to ensure that the atoms are very close to one another. And the situation where the atoms are very close to one another is when they participate in bonding. There is no other situation at all. No other situation at all. And in chemistry, there is no one bonding. Some people do it as a covalent, some people ionic, some people don't participate, some are metallic. So instead of one definition of atomic radii, I'm forced to what? Introduce to you four operational definitions for atomic radii, that is covalent, ionic, van der Waals and metallic. So students, once they open the textbooks, they might feel that you have four atomic radii. Why four atomic radii? Why not one? Because those are all the difficulties which I'm projecting it to you. You can't escape. Hence, we are not escaping, but we are proposing all this, and all these measurements of atomic radii will be having errors. Now, the details of all the four will be given to you in the next class. My appeal to all of you is, follow me, follow Tone Academy, follow T1 channel, bank on us, because we will be following the sequence, and every subtopic I'll be linking this to the JEE or the pre-engineering test. So just relax at any point of time, just to click on the T1 channel, Tone Academy, subscribe, and I'll be there. Along with me, we host the best faculty available for you. Thank you and thanks for listening.